plane motion. Okay, if you take this diagram, right, first diagram, so you can assume that as a disk, right, a disk which is rolling in a plane. So in disk there can be number of particles. So you know this is compiled by number of particles all over this plane. Okay, so these arrows, they are indicating the motion of each particle, right? So a particle, you know, if it is somewhere here on the edge, that would have the motion which is tangential to the surface. So if I can draw, so the tangent would be from the center to this point. Okay, so the motion of these particles which are actually at the edge would be perpendicular to not perpendicular, tangential in the sense, right? At the same time, right, this disk is rolling as well as moving forward, right? So if you consider this disk which is rolling at the same time which is moving forward also, so the disk itself will have a forward motion. So the particles which are present in this disk will have a forward motion as well as a rotational motion. So these particular arrow marks are the motions of each individual particle, right? So these all particles are moving in a particular plane. So if I consider this as y and this as x, right? So we can define the motion of any of these particles in this xy plane, right? So we'll take another example. So this is a kind of a hanging object. So from a roof or something, the object is hanging. So which is making a motion this way, right? So all the particles which are in this plane or in this object will have a motion towards this direction, right? So I can define that motion in xy plane, right? Xy plane. So plane motion mean the motion which is actually occurring in a particular plane which does not need z-axis, right? So which does not need z-axis to define, because if this particle move to this position when it is swinging, right? Or I'll take this particle which actually move to this position. So in this sense, I don't need z-axis to define the motion, right? X and y axis is enough, right? So this is what called the plane motion is, right? So here it's again a complete rotational motion. So all the particles which are at the edge would have a motion which is tangential to its circumference, right? So this motion also we can define with the help of two axes, right? X-axis and y-axis, right? So this is what called as plane motion. So in plane motion, what actually happening to the particles? So I show you the two examples, right? First example, a disk is rotating. The second example, an object is swinging, right? So I'll take an object swinging that example, okay? So in that case, it is going to swing like this, right? So in that case, a particle which is here will move here, right? A particle which is here will move here. A particle somewhere here will move here, right? So after certain time, our object would be in this plane, right? So this would be the new position after some time, okay? So each particle here would have moved to the new position, right? So this particle will be moved to this position, this particle will move to this position, and this particle will move to this position, right? So in this sense, all the particles are exhibiting a linear motion, right? Linear motion. You see all the arrows are linear. So this type of motion we call it as rectilinear translation, right? So each particle will move by certain distance to a new position in a straight line, right? So which we call as rectilinear translation. Okay. We have another type of motion, that is curvilinear translation, right? So in the first diagram and the diagram, if you see the particles, right, which are in this object have moved by some rotational angle. So in such case, we call this motion as curvilinear translation, right? So for example, if a particle which is in this position may have come to this position, it might have come to this position, right? A particle which is here, it might have come to this position. So if you take the individual motion, they are exhibiting a curvilinear motion, a kind of curved path, right? So that's why curvilinear translation, right? So you see curvilinear translation, right? So these are the two motions possible in the plane motion, a kind of rectilinear translation and curvilinear translation, right? So space motion. So at the beginning I told you there are two type of motion, right? One is plane motion, the other one is space motion. So this one, if you remember in childhood, you might have played with this toy, right? So if you spin it, that will keep on spinning as well as swinging, right? So that would be in different shapes. Something like this would be there in the tip. Do you remember? So if you swing it through this axis, this will spin as well as it will swing. So these type of motion are defined said as space motion, because here two axis is not enough to define the motions. If I draw an x-axis, a y-axis, so if it is only moving this way and this way, x and y is fine. But what actually happen is it is spinning about this axis also, right? So in that case, I need a z-axis also, right? So it is rotating about its own axis, right? So this is its axis. It is rotating about its own axis as well. It is swinging about an axis here, right? An axis which are here. So this motion need more than two plane to define its motion. So if I take a particle, I need three coordinates to define that particle. Say for example, if I am taking a particle somewhere here, I need an x value, I need a y value, as well as I need a z value. So this is why it is called as space motion. Okay, now we'll see what actually happening while in a motion. So how a motion can define with minimal effort, right? This is its initial position and here it's final position, right? So this is the final position. So what actually happened is, right, the object is moved to this position in a straight line, right? You can move it. Similarly, this end would become here and this end will go there, right? So you can move this object to this position in a straight line, right? So along this line, this object is moved to this position, and then about this axis, right, about this axis, it is rotated, right? So if you consider this one as the point, about this point it is rotated. So that will act like, so now this point is here, but this point move to this position, this point move to this position, and this point move to this position. Okay, but this point is kept constant because about this point only it is rotating. So you can consider this as the axis, right? So about this point it is moved from here to here, this point to here, and this point to this position, right? So a motion, right, a movement can be written with minimal effort as a straight line motion plus a rotational motion, right? So these two terms, a straight line motion and a rotation motion, is enough to define the motion of any objects, right? Any objects, right? So if you consider this object now moved somewhere here, so what actually happened, this is actually moved to this position, but there is no rotation, right? So what happened here is a pure straight line motion. You see, right? There is no any rotational motion. But if I draw this object in this way, after it moved here, about this point, there is a rotation has taken place, right? So about this point, a rotation has taken place. So this point moved here, this point moved there, and this point moved here. What I want to say is a motion can be defined with two motions, right? That is one rectilinear or straight line motion plus a rotational motion, right? So these two terms are enough to define a motion. So now we will see what is the effect of what I have seen here in the motion of the body, right? Force and couple of a link. So you take any arbitrary body, right? Any arbitrary body. Say this is your body, right? A force is acting on that. Okay, a force is acting on that. G is the center of gravity point. So you know all the objects which have mass has a center of gravity point where the mass is considered to be acting on, right? So if you consider all individual particles as like small pieces, right? So this complete body is made up of tiny particles, right? So I can divide it into tiny particles. That's how actually it is made up of, right? So for my easiness, I am drawing into these big sizes, but these are actually tiny particles. So each particle has its own center of gravity, right? So this small piece has center of gravity here. This small piece, it has the center of gravity here. This small piece which has center of gravity here, right? When you combine everything, right, all the small particles, where the actual center of gravity is acting is the center of gravity of that particular body, right? So in this case, in this body, the center of gravity is acting in this particular plane, not plane, point. So there are numerous number of points, right? There are numerous number of points. How are we going to determine where actually the center of gravity point is? How do we know this is the center of gravity? Why can't it be somewhere here or somewhere here? So we integrate, right, all these points, right? So integration is little bit added, right, giving the boundary conditions, right? So from this point, I mean this plane to this plane, or this plane to this plane somewhere, right? So what you do, you take these each individual points and you will integrate it, right, with having two boundary conditions, right? So from this to this or this to this, that's up to you, right? So when you have it, by adding this all these points, you will have a mass and a distance from where you take it. So if you take this as a base point, that will give you a distance where it is acting, right? So through integration, we can find where the actual center of gravity point is, right? F1 and F2 equal and opposite forces acting through G parallel to F, right? Before that, this is an F, that is force, right, which is acting a distance h from the center of gravity, right, and h from the center of gravity. This force F can be replaced by, right, so if I add one F here and one F here, these two are in equal in magnitude, right? So I say F1 and F2 are equal in magnitude. So in such case, this F2 and this F1 will be cancelled out, right? So there won't be any net force. Okay. So I will draw this diagram again. Assume that's the same diagram, right? Even if it is not. So here I have a G, here I have an F. This is given data, which is acting in a distance h. This is perpendicular distance from G to this F, that is perpendicular distance. So these are given data. So what I do is I will add one force here and one force here without disturbing the equilibrium of the system, right? So instead of putting F1 and F2, I'll put F1 because both are same in magnitude. So by inserting these 2 points, right, by inserting these two forces, there is no change in the system because this F1 and this F1 would be cancelled out. But why we do this is, okay, to transfer this force to this position, right? So now if you see, F1 and F2 equal and opposite forces acting through G parallel to F, right? Yeah, and direction also, this and this should be parallel, okay, and acting through G, resultant of all the forces acting on the rigid body. So this F is resultant of all the forces acting on the rigid body, and H is the perpendicular distance between F and G. So F is the resultant of all the forces, G is the center of gravity, and H is the distance between these two, and M is the mass of the rigid body, right? M, mass of the rigid body. So if you consider any rigid body, rigid bodies will have some mass, right? Mass of the rigid body. So what actually has happened is you transform this force to here, right? So this force to this location, and you created a couple, right? Created a couple. You see, a distance and a motion, so that will create a couple. So from a point, a force into distance, which will create a couple, right? So a force which is acting anywhere in a body can be transformed to the center of gravity as a force and a couple, right? A force which is acting anywhere on a body can be transformed to the center of gravity as a force and a couple.